Hi everyone, this is Deepak. I'm here to um, display or present my Data 605 final exam for Spring 2019. So we'll start right away. The first question is, using R, we have to generate a random variable X that has 10,000 random uniform numbers from 1 to n, where n can be any number greater than 6, and then we'll generate a random variable Y that has 10,000 random normal numbers with a mean of mu equal to sigma equal to n plus 1 by 2. So we'll go right away to the RPubs. So the first step is to attach or import all the packages that will be required in the whole exam, and then we'll start right away. So we have defined 10,000 10,000 uniform numbers from 1 to 10. I've taken n equal to 10, and then I've created the variable y with 10,000 numbers in the normal distribution, having mean and sigma both equal to n plus 1 by 2. Here I've calculated the median of x, that is my uniform numbers. It comes out to be 5.45, and then first quantile of the y, which is my random normal numbers. So the first quantile comes out to be 1.826. So now I've created a data frame out of both x and y, and I've called it xydf, and I'll be using it further. So moving forward, the first question is to find the probability of x greater than x given x greater than y. So it's like a conditional probability. So we'll use the formula for the conditional probability. Here the formula comes out to be p x greater than x conditional on the condition x greater than y will be equal to the conditions of both divided by the probability of my second variable or the second event. So which is p x greater than x and x greater than y divided by p x greater than y. So it comes out to be length of x greater than x and x greater than y by length of x whole divided by length x of x greater than y divided by length of x. So it comes out to be 0.55. So that means 0.55 is the probability of this event to be true. Coming to point B, we have to find p x greater than x and y greater than y. So it's like an and. The comma denotes the and. So we use the formula p a and b equal to pa into pb, as both are independent events. So I've calculated the first probability here and then second probability, and then I multiplied each of them to give me this whole probability. So it comes out to be 0.375. Next question is p x less than x given x greater than y. So here again I'll use the formula, which is p x less than x and x greater than y divided by x greater than y. So it comes out to be 0.449. Okay, moving on to the next question. We have to investigate whether p x greater than x and y greater than y equal to p x greater than x into p y greater than y by building a conditional building a table, which is a contingency table. So we have created the data frame, and we'll use the data frame. And so in the first step, I've created the contingency table where I've used x greater than x, y greater than y, my first variable, x greater than y less x greater than x and y less than y, my second variable, then x less than x and y greater than y, then x greater than x less than small x, and y less than small y. So, and I put it in a form of a matrix, which is my contingency table, and I've called it rows and columns appropriately. And now we'll calculate the left hand side of the equation, which is p x greater than x and y greater than y. So if you see here in the contingency table, this is my value which I need, divided by the whole number of observations. So it comes out to be 3749 by 10,000. It's 0.3749. And then on the right hand side we have px greater than x into py greater than y. So here we already calculated these two above in the upper questions, so we'll use them, and then we are multiplying both of them, and it comes out to be 0.375. So if we compare these two, both of these come out to be very near or nearly equal, so we can say these are independent events. That's why P A and B is equal to PA into PB. Okay, moving to the next question. So we have to check if the independence holds true by using the Fisher exact test and the chi-square test. Okay, so we have defined the null hypothesis that x greater than x and y greater than y are independent events, and the alternate hypothesis will be both of these are independent events. Now the contingency table that we created in my previous question, we'll use that, and we'll use the straight formula Fisher test in R, and when I run this formula, it will give us the p-value which is of important use to us. So it will define. So here the p-value is very high as compared to our normal significance level of 0.05. So that means we can easily reject the null hypothesis that both the events are independent. So hence we can say easily using the Fisher test that both of these events are independent. Now we'll use the chi-square formula given in R, chi-square dot test, and we'll use it on the contingency table, and the p-value comes out to be 0.9816, which is exactly same as the Fisher test in this scenario. So again we can say the p-value is very high, so we can easily reject the null hypothesis, and that we can say that using this both these events are independent. Okay, so now moving on to problem number 2. So we are asked to register on Kaggle.com and compete in the house prices competition. It's a regression techniques competition. The first point that we are asked to do is we have to provide the univariate descriptive statistics and the appropriate plots, and then we plot some scatter plots, then we'll use some correlation metrics, and we'll show the hypothesis. So moving forward, basically first point is I'm importing my data frame, my train data frame from the Kaggle.com, and then I've just showed the header here so that it will show all the variables. So we see that the number of rows is 1460 on the train data set, and the number of columns is 81, including the response variable. So our response variable here is the sale price, and all the other 80 variables are kind of independent variables which we'll be using to determine how many of these we should be using in our regression model to predict the sale price. Now we've given here so we are taking the numeric variable, only the numeric variables from our main data frame, and creating another data frame which is called train df numeric, and we've used only the numeric variables out of that. And then we are using the fbasics package which will help us create the basic univariate statistics of each of our numeric variables which we have chosen. So we are using the function basic stats here from fbasics package, and we are taking all these important statistics for each of these numeric variables. We use the minimum, the maximum, first quartile, third quartile, mean, median, variance, standard deviation, skewness, and kurtosis. So all these will help us in our future analysis. That's why we have taken it here. And moving forward, um, we are creating here the box plots of all of our numeric variables. So I'm using the normal simple box plot function from the basic R for all of these numeric variables, and then I'm basically trying to see how all these events ranges are defined in our data set. So it will give us an idea. These are very good plots which will give us an idea uh, which of these are right skewed or left skewed or nearly normal. Like if you see we go to the top of this and we see the year build. This looks to be a left skewed one because we have some variables here, though not very much, but still there are a few. Now this one, mass VNR area, it looks to be a very much right skewed variable, and this one too, and so on. So these box plots give us a good idea whether these variables follow a normal distribution or left skewed or right skewed. So we'll move forward now. We're, we're trying to draw some scatter plots between the response variable and few of the independent variables. Like we've defined here the scatter plot between lot area and the sale price, and it looks to be a very decent um, decent regression line. These look to be quite dependent on each other. That means sale price looks to be independent on the lot area. Of course, the slope is very huge, but still it looks like. So moving forward, if we see, this is the scatter plot between the BSMT fin SF1 and Y sale price. Moving forward, we'll just open the description of all of these quickly. 1 second. I'll go to kaggle.com. I'll log in. And I'll go to my competitions. Go to the data. So this is our description, like all the variables have been defined here. We can probably use this to understand what all of these variables mean. So now moving forward. Okay, so this is between the GR living area, which is the living area above ground, versus the sale price. So it looks like sale price is highly dependent on the living area above the ground. This is between the garage area and sale price. Okay, now we'll define the correlation between lot area, living area, and sale price. So the first one we'll define between living area and the sale price. The correlation seems to be 0.7, and then the correlation between the lot area and sale price comes out to be around 0.26. And now we'll go back to the question. So we'll have to basically suggest test the hypothesis that the correlation between each pairwise set of variables is 0 and provide an 80% confidence level. So my null hypothesis is that correlation between y and z equal to 0, and my alternate hypothesis is the correlation between y and z is greater than 0. That means they are related to each other. So I'll use the 80% confidence level. So this we'll use a t-test here, and then we see that 80% confidence level that the difference in the means of two variables is between minus 182071 and minus 176740. So the p-value comes out to be very less. Hence we can reject the null hypothesis and say that the correlation between living area and sale price is not zero. That means these are related to each other. And in fact, p-value of such a low value indicates that these are highly related to each other. We'll see this relation further in our regression model in a further question. Moving forward, we'll do the t-test on x and z. That means the lot area and the sale price. And my null hypothesis is that the correlation between x and z equal to 0. And my alternative hypothesis is that the correlation is greater than 0. That means these are related to each other. Now we'll run the same formula test, t-test, and we see that the p-value here is also very less. That means these two variables are related to each other. They have a correlation of greater than 0. And 80% confidence level of the difference in the two means will lie between this minus 173091 and minus 167717. So that means these two are also related to each other. Okay, the next question is related to linear algebra and correlation. So we are using the correlation matrix from our above questions. Basically, here I'm creating a correlation matrix of the variables we used above, x and z, that is the lot area and sale price, and then this is our correlation matrix which comes out to be, and then we'll take the inverse of the correlation matrix, which is the precision matrix. So we are using the inbuilt R function solve, and this comes out to be our precision matrix, which is inverse of our correlation matrix. And to we'll then multiply the correlation matrix with the precision matrix, which are basically inverse of each other, as we calculated the precision matrix as the inverse of correlation, and it comes out to be an identity matrix. Similarly, we'll run the other way around the multiplication, the precision matrix first and the correlation matrix second, and then it comes out to be again the identity matrix. Now we'll use the LU decomposition. So basically we are doing the LU decomposition on the matrix, on the correlation matrix that we used above. So L comes out to be this, and then U comes out to be this. If you multiply both of them, they give us our correlation matrix, as we use the formula on our correlation matrix to find L and U. Okay, so we check the identical whether my correlation and the multiplication of my L and U which I derived are same, and they come out to be same. It should be. Okay, moving forward. Okay, so here we are basically asked to fit an exponential function. I'll quickly go to the question once. So basically we have to fit an exponential probability density function to our variable using the fit distribution function from the mass package. So we've already imported the mass package, and then first we'll just see how the lot area looks like. It's a very much rightly skewed variable, as we were asked to do. So I've just created a histogram of the lot area and it comes out to be this, which clearly says that it's a rightly skewed variable. So now I'm basically fitting an exponential distribution to the lot area variable, and then we'll find the lambda here. We got the lambda, and then it comes out to be this value, and then we'll use the lambda variable to generate the exponential variables. We are asked to create 1,000 random values with the exponential function using the lambda that we derived from above, and then we'll create a histogram for that. And now as we see, this looks to be a exponential distribution after we fitted the variable to this exponential distribution. Okay, moving forward. So plot a histogram and compare the histogram with the original value. Using the exponential PDF, find the 5th and 95th percentiles. So we are finding here the 5 percentile and 95 percentile values using the QEXP function and the same lambda. So these come out to be these values, and then we're generating 95% confidence level assuming that the distribution is normal. So we'll use the QNorm function here, and then we are generating the 95% confidence level. It comes out to be lying between these ranges. Then the actual data, basically we are asked to use the empirical data, that means the real data, to get 5th and 95th percentile. So we'll use the quantize function and use our data set variable, and we are generating the 5th and 95th percentile. So that's all we need to do in that question. Moving forward, we have to create a multiple regression model, and then we are asked to submit the same model or the results on the Kaggle competition board, and then we'll generate we'll fetch the score from there and we'll paste it. So I started with, so basically we'll start with all the numeric variables that we have, and then step by step we'll remove some of them based on how the model looks like. So in the start I've used all the variables, that's why I've used start here, and then it comes out to be this in the summary. So the summary gives us a very good idea of what all variables should we be using. So all the variables which have the p-value of greater than very high, which is very higher as compared to 0.05, which is the general significance value, then we'll remove all of such variables, and then we'll remove all the NA ones. That means they don't have any direct relationship with these variables don't have a direct relationship with the response variable. So I've used only the variables which have the p-values which are less than 0.05 or very near to 0.05, and then we'll see the new model how it looks like. There are still some variables which have the p-value of greater than 0.05. So as per the backward elimination multiple linear regression model, we have to remove the variables which have greater than 0.05 or the significance level p-value, and then further we'll remove all such variables again. So we have created a new model, and then let's see here. So we still have a couple variables which have p-values of greater than 0.05. So we'll remove those two variables as well. And now all the variables look to be having the p-value which is less than 0.05. There are still few which have p-value of not very less, like 0.02. That's why it is a single star. So single star, double star, 3-star. So 3-star means they have a good relationship with the response variable. That means it has a huge dependency, and the response variable has a huge dependency on that particular variable, which shows the 3 stars. So now we are good. We'll use this model as our final model for now, because all the variables have the p-value greater than very less than 0.05. Okay, so we'll use that our final model, and we'll now um, use the test data from the same Kaggle data set or the location, and we'll predict the values of the sale price now. So we'll use the predict function of our same final model that we created, and we're using the test data frame, and then we're getting the values here. So in the end, I basically extracted or write my prediction results data frame into a CSV file, and then I uploaded it on Kaggle, and my Kaggle score came out to be 0.514. This is my user ID, and that's all we were asked to do in this question as well. So we are done with the exam now. Thank you so much.